So this video lecture is going to be about population dynamics. So far we've learned about, which populations eat who, how energy consumption. Then we learned about reproduction and population counting and where all that's going to play a role in terms of the ecosystem. Now we're going to talk about population dynamics. And the key here is the word dynamics. And dynamics means change. So how are populations changing? So in the previous unit, we talked about counting and population estimates and things like that. But then we need to understand that those numbers are constantly changing all the time due to deaths, due to births, due to disease, and all sorts of different things that can happen. So we want to know what factors affect population dynamics. So what types of things are going to cause a population to change? What are those factors that are going to play a role in it? So first one, pretty obvious, is births and deaths. Okay, new species being born, that same species dying. Well, that's going to play a role in the population count. So there's actually a really simple equation that we're going to use for this, and pretty straightforward here, that R is the population growth. That's how much does the population change by, and is given by the number of births minus the number of deaths. So for instance, if we had a species that had 100 births in a given time frame and it had 75 deaths in that same time frame, well, the R value, the population growth, would be plus 25, right? You have 25 more species than you started with. However, instead, maybe you had only 25 births in another time frame for different species, and you had 50 deaths in that same time frame. Well, then you had a population growth of negative 25. So if birth outweighs death, then you're going to have population growth. If the deaths are greater than the births, then you're going to have a negative population growth or population drop. Pretty straightforward. That really makes sense. So what's one of the other factors? Well, it's reproductive strategies. What does that mean, reproductive strategies? Well, there's two major strategies that we're going to refer to here. One is an R strategist and one is a K strategist. And you see the fly falls into the R, elephants, other large mammals fall into the K strategist category. And what's the difference here? Well, in an R strategist method, there's lots of offspring and very little care. A fly is going to come around, it's going to lay, maybe it lays 10,000 eggs, right? Has 10,000 little eggs going around, and maybe 9,500 of those get eaten. Well, that means there's still 500 flies left. Okay, so even though 95% of the flies were fly larvae were eaten by something, there were still 500 flies left that were born. Okay, and the key here was there was no care whatsoever. Okay, they put 10,000 eggs down, lost 9,500, 500 grown, and the fly didn't care. The fly was gone. But the species perpetuates because, well, you still got 500 births, even though you had a 95% kill rate of the eggs that were laid. So that's one strategy. The other strategy is basically just by pure numbers. Okay, put as many offspring you can down, and some of them are going to survive. K strategists, however, have very few offspring and lots of care. So an elephant might give birth to 12 elephants its entire life, but 11 of those 12 are going to make it, okay, because it's going to take care of them. It's going to spend 13 months in gestation. It's going to spend years raising it. Once it's been born, teaching it how to survive, teaching it the tricks of being an elephant, what it means, how to survive in any kind of environment that they're going to be placed in. And all of that care is going to go into making the fewer offspring more productive, more likely to survive, more likely to make it, more likely to perpetuate the species. So neither of these strategies are better. They just approach it differently. Okay? Our strategist bombard with as many eggs as possible, as many offspring as possible, forget about them, go away, and hope as many survive as can. Just purely based on numbers. K strategist is, hey, we're going to care for our young. Hey, we're going to spend a lot of time with it. It's going to take a lot of time, a lot of effort, a lot of energy, but we're going to make sure that that offspring survive. So you'll need fewer of them to make sure the species perpetuates, but you will also have a much higher percentage of success rate in terms of those offspring making it. So those are two different strategies, okay, for reproduction, okay, that we'll see in the animal kingdom. The next category is getting into this concept called sexual maturity. And that's basically, when does an animal or species reach the point where it can actually give birth? So here's two red fish species. They look like red fish. They're out in the ocean. We have the Notobranchius cadlecki and the Hoplostetus atlanticus. Okay, both fish out in the ocean, and we might want to think about, well, when can they actually start to give birth? Well, for the Notobranchius cadlecki, it can give birth in just 17 days. Think about that. It's going to allow it to expand its population a lot faster. Okay? Its numbers will grow much quicker. Okay? It will have a much greater dynamics because, well, 17 days after it's born, it can produce more offspring. We can get more of that fish. However, with the Hoplostetus atlanticus, that's got a 30-year period before it reaches sexual maturity. So it's not going to be able to breed any more fish for 30 years after it's born. You're not going to be able to grow your population very quickly there. Okay? You're not going to have a lot of population dynamics. Things aren't going to change fast because it takes so long for for the species to be ready to actually produce more of it. So this concept of sexual maturity plays a big role in terms of how quickly you can reproduce, in terms of how quickly your population can change, because that time it takes to reproduce. So you think with humans, and we're talking about when you hit puberty, that's your point of when you're reaching sexual maturity. You could produce another human at that point in time once you hit puberty. So like 12, 13, 14, 10, 11, 12, 13 years, okay, that's the time frame that we have. So we're a slower maturity rate than, say, a mouse, which can, within a span of a couple months, be ready to go and produce more mice. So that leaves mice with a much greater chance for having greater population change than for humans. Okay, but again, few children, more intense caring could mean a greater survival rate for human children than like a mouse. Okay, great. So we have these three factors that are going to affect how quickly populations can change. We have the population growth rate, we have the how quickly you reach sexual maturity, and we also have how the type of strategy used for sexual reproduction. But then how do these populations grow once we implement these strategies? So in theory, population should grow exponentially, right? Start with 2, then 2 is going to split into 4, which is going to split into 8, which is going to split into 16, so on and so forth, just exponentially growing for as long as possible. Okay, but in reality, what ends up happening is you do have that exponential curve early on, and it continues to grow and grow, and then it's going to reach this thing called the k-value up here. This is called the logistics curve. I'll talk about what that k-value represents, and it represents what's called the carrying capacity for an environment. So you think about it like this. You have a population of deer, right? They move into a new location, and there's not many predators in there, and they start to eat, and they're like, oh my gosh, this is the best, and we're just going to keep growing. We're going to make more and more deer because there's not many predators, there's lots of food, but then all of a sudden they hit a point where they pass what's going to be the eventual carrying capacity of that location. So the population starts to slow down because maybe predators moved in, okay, maybe predators came in, the food supply dwindled, water supply dwindled, all of that stuff affected how many deer that this area could hold. So all of a sudden there's some starvation, some of the deer leave, predators start to attack more, okay, and the population starts to drop. and then it bottoms out. Okay. At that point, maybe the predators have started to the food starts to grow back, the water supply comes back, the predators have now left, and then the population starts to grow back up again. Okay. And it's going to kind of squiggle around this K value until it's eventually steadies out. Okay. Assuming that there's no major changes, and eventually kind of comes to rest near that carrying capacity for that environment. So you might have to analyze some of these graphs on a test. Let's see here, we have two different species grown separately, and they have their population curves where they K-value out over 10 days. And then we grow them together, and all of a sudden you see that one of them has a population that drastically drops off early on. So that tells you something about the interaction between these two species. Okay? One of them continues and thrives, the other one dwindles and dies off over the time frame because there's some kind of interaction between the two. And you might want to be able to analyze that graph on a test, think about why that might be happening. So some factors that do limit growth. So these are important things to understand. We have things that are called density dependent factors, and we have things that are density independent factors. So it's important to understand the difference. Density dependent factors depend upon the density of the animal, right? So if there's one cow in this field could probably last forever, but as soon as more and more cows move into it, the grass is going to grow away, the water supply is going to grow away, okay? The predators are going to start to move in, okay? These are density dependent factors, things that will depend upon how many animals are in that given location, okay? So the greater the number of cows in that field, okay, the more resources that field is going to require to handle that, and eventually you're going to hit a cap where it cannot withstand that population. Okay? However, there are also density independent factors. Okay? If these natural disasters are great examples of this, say these cows move into a location near a volcano, that volcano blows up, lava spews everywhere. It doesn't matter if there's 1 million cows or 5 cows. Those cows are going to die. They're going to get burned up. Their food sources are going to get destroyed by the lava. Okay? Though that is independent of how many cows are there as to what's going to happen in the cow population. So it's good to understand what categories these things are going to go into. That's one thing you're going to want to think about. Does competition, stress, disease, sunlight, drought, building dam, predation, are those density dependent factors or are they density independent factors? And that's something you're going to work through in some of the following activities.